Okay, in this tutorial we're looking at section 5.3, which is talking about I and J notation for our vectors. Okay, so to start off with, we need to talk about our unit vectors. So a unit vector has a magnitude of 1. Unit vectors have a hat or a circumflex above them, so e.g. a hat. Okay, so you still need our tilde underneath and a little hat above it. If A is a vector, then its magnitude is given by the modulus of A, and our unit vector is equal to our vector A divided by the modulus of the vector. A unit vector in the positive direction parallel to the x-axis is I, so our x-axis has a I unit vector, our y-axis has a j unit vector, and our z-axis, our other page, if you like, is the k unit vector. So I, j and k notation. Since we know I, j and k are unit vectors, we don't put a hat on them. Okay? So I, j and k are our universal ones that we use to represent unit vectors, so we don't worry about putting this hat on there. Okay? Any other time we need to put the hat on there to distinguish them. If a vector is expressed as a multiple of either I, j or k, it means it is parallel to the appropriate axis and has a magnitude that is equal to the coefficient of either I, j or k. So what I mean by that is if we have 3i, what that means is we have a vector that is parallel to the x-axis that has a magnitude of 3. So we'll keep moving on. This one's quite a long section, so there's a fair bit to get through. So position vectors in 3 dimensions. So we represent points in 3-dimensional space. Okay, and remember that I is the x direction, j is the y direction, and k is the z direction. Any point or vector in 3-dimensional space can be expressed using a combination of unit vectors from a given point, or the origin. So if we say the origin here, in our x direction, now I know I was just saying before that we were saying that we had x, y, and z. But by convention we actually often draw it a different way, and that's with x coming out on the page, y coming across, and z coming up. I'm not sure why that convention is the way it is, but often you'll see it drawn like that instead. The thing to remember is that I is with our x, j is with our y, and k is with our z. And we take them from our origin. The magnitude of a position vector, OP, so if we have some vector like this, so think of it coming out of the page, and we say that's P. So what we can do is we can map it down to some point here. So we'd end up with some x value there, some y value there, and some z value there. So the magnitude, the length of this vector, OP, is given by, well, it's really our 3-dimensional Pythagorean theorem, which is that it's equal to the square root of x squared plus y squared plus z squared. Now remember there, the x, y and z are all just coefficients of I, j and k. So we'll keep moving on. So if we talk about addition and subtraction of vectors in 3 dimensions. If A is the point x1, y1, z1, and B is the point x2, y2, z2, relative to the origin, then OA, so the origin to A, is x1i plus y1j plus z1k, and vector OB, so that's from the origin to our point B, is x2i, y2j, and z2k. And then, if we're going to add OA and OB together, then all we do is we add our coefficients. So we say x1 plus y1i, y1 plus y2j, and z1 plus z2k. So it's not too bad. So we've got 2 points, and we say the vector is from the origin to those points. If we're going to add those vectors, then we just add our coefficients of y together, and our coefficients of j and our coefficients of k together. If we're going to say that we have some vector AB, which is equal to the vector OB minus OA, then it just becomes x2 minus x1i, y2 minus y1j, and z2 minus z1k. Right? So AB is the position vector of B relative to A instead of the origin. Okay, so saying AB is the position vector, okay, relative to A instead of the origin, where our position vector OA was from the origin to A, AB, okay, is from A to B instead. And the modulus of AB, okay, same as what we were talking about before, it's our 3D Pythag work. Okay, it's the square root of x2 take x1 squared plus y2 take y1 squared plus z2 take z1 squared. Okay. So flip over and we're going to have a look at a worked example. Okay, so we're saying if the point P, okay, has the coordinates 3, 2, minus 4, okay, we've got to find the vector OP. Okay, so what we do is we say, well, this point here has the points x equals 3, y equals 2, and z equals -4. So we say, well, OP then is going to be defined as 3i plus 2j take 4k. So these points are just our coefficients of I, j and k. And part B, okay, is we want to find a unit vector parallel to OP. Okay, so we need to find the length of OP to start off with. So the magnitude of OP is going to be found by doing the square root of x squared plus y squared plus z squared, which is going to equal the square root of 3 squared plus 2 squared take 4 squared, okay, or plus -4 squared, which equals the square root of 29. Okay, so that means then the unit vector, okay, remember our unit vector is found, so OP hat is going to be found by OP over the magnitude of OP. Okay, we talked about that earlier. Okay, so that just means that we've got this vector divided by our magnitude, or our easier way to write that is that OP hat is equal to 1 on 29 outside of our 3i plus 2j take 4k. That's our easier way to write it. Okay. Alright, so we'll keep moving on to equality of vectors. So if A is x1i plus y1j plus z1k, and B is x2i plus y2j plus z2k, so two vectors there, A and B, then A equals B if and only if x1 equals x2, y1 equals y2, and z1 equals z2. That makes sense. Okay, of course these things are only going to be equal if our coefficients of all our terms are the same. If one of those terms is different, okay, then it's not going to work. Okay, they're not going to be the same. Okay, we talk about scalar multiplication. Okay, so A equals x1a plus y1j plus z1k. Okay, then some lambda times A, so it's just some value lambda. It could be any number. Okay, and we're saying it's just a number, okay, so it's a scalar multiplication. Then that's going to equal lambda x1 I lambda y2j plus lambda z1k. So we just multiply each of our coefficients by the coefficient of our vector. Okay, and parallel vectors, two vectors A and B are parallel if A is some multiple of B. So again, we're saying A equals lambda B, so lambda is just a number, so it's saying A is some multiple of B. So that is if A is a multiple of B. Okay, so we'll have a look at a worked example again. Okay, so what we're going to look at is, we're saying, well, A is equal to 2i take 3j plus zk, and we've also got B equals 4i take 5j take 2k. we want to find the value of z if the vector c, so c is equal to 3a take 2b. Okay. So what we need to do is start off by going, okay, well, we need to actually work out what 3a and 2b is. Okay, so we can say, well, our vector c is going to equal 3 times 2i take 3, so 3j take zk minus 2 lots of 4i take 5j take 2k. So what we're going to do there is we can expand our brackets and say that, well, this is going to be equal to 6i take 9j take 3zk take 8i plus 10j plus 4k. And so what we're going to do is we can then bring together our coefficients of our I and our j's, so and say, and our k's. So and say, well, we're going to be 6 take 8 is going to leave us with negative 2i. Okay, and then we can say, well, our negative 9j plus 10j will leave us with 1j. And then we can say we've got minus 3zk plus 4z, plus our 4k. So I've made a little mistake here, and they've said that it's plus, so we minus 3z plus 4. Okay, they've made a little mistake. No, sorry, it's my mistake. I was plus up here. So we should have been plus and plus, so that will be plus still. Okay. Right, and then what we do is we say, okay, so if this vector is parallel to the xy plane, okay, which was part of the question, okay, so we're saying that find z if this equals this and it is parallel to the xy plane. Well, that means that our k part has to be 0. So we say, well, 3z plus 4 equals 0, so the z has to equal minus 4 on 3. Okay, so we'll keep moving on. So we now talk about linear dependence. Okay, so we consider 3 vectors, a, b and c. A, b and c are linearly dependent, okay, if we have some value alpha times a plus beta times b plus gamma times y equals 0. So saying that we're multiplying a, b and c by constants, and that all of those constants don't equal 0. So saying this overall has to equal 0, but our constants can't equal 0, then it's called linear dependent. Okay, if alpha a plus beta b plus gamma c equals 0, then we can write c equals na plus nb. That is, that one of the vectors is a linear combination of the others. Okay, so I'm going to say that one is a combination of the others. Okay, where m is minus alpha on gamma and n is minus beta on gamma. So all we're saying is put our c across the other side of our equation, divide each one by gamma, okay, or minus gamma and b, okay, to end up with this equation. So we're saying that, and you could do that with any 3 of your letters. Okay, if alpha a plus beta b plus gamma c, okay, equals 0, okay, if and only if alpha, beta and gamma equals 0, then a, b and c is said to be linearly independent. Okay, so if the only way that these equal 0 is if alpha, beta and gamma equals 0, then they're independent, linearly independent. Okay, and we'll have a look and work an example about that. So we're going to show the vectors a equals I minus j plus 4k, and b equals 4i minus 2j plus 3k, and c equals 5i take j plus zk. So we're showing that the vectors A, B and C are linearly dependent, okay, and determine the value of C. Not C, of Z. Okay, so what we need to do is say, well, we should be able to write it as C equals MA plus NB. Okay, so that's what we should be able to say. So what we do is now sub in our vectors into the appropriate places. So we can say that we should have 5I take J plus ZK equals our M outside of our A. So M outside of I take J plus 4K plus N outside of our B, which is 4I take 2J plus 3K. Then what we want to do is expand out our brackets, okay, and say that we've got MI take MJ plus 4MK, okay, plus 4NI minus 2NJ plus 3NK. So what we say then is what we can do is match up our coefficients. Oh, sorry, before that we've got to collect our like terms, sorry. So we need to say then that we've got, we can say that we've got M plus 4N plus 4NI, and then we've got take M plus 2NJ plus 4M plus 3NK. Right, now what we can do is match up our coefficients. So we can say, well, 5 has to equal n plus 4n. Okay, and we can also say that our minus 1 equals minus m minus 2n, okay, because we need to match these up properly. Okay, and then we can also say that our z equals 4m plus 3n. Okay, so if we add these two together, okay, say 1, 2 and 3, so we add 1 and 2 together, then we're going to get 2n equals 4, so n would equal 2. Okay, and then if we have a look back at this one here, okay, and so n back in, we get 5 equals, we rearrange for m and say, well, we get m equals 5 minus 4n, so then say we get 5 minus 4 times 2, so m equals 5 take 8, which is minus 3. Okay, so now we can put in our m and n values into here and find our z value. So z equals 4 times our minus 3 plus 3 times our 2. So z equals minus 6. Okay, and we're finished off. Right, so we'll keep going here. Okay, so we've got direction cosines. Okay, so we're saying if we've got some vector OP, and that's the vector x1i plus y1j plus z1k, then alpha is the angle between our vector OP and the positive x-axis, beta is the angle between OP and the positive y-axis, and gamma is the angle between OP and the positive z-axis. Now I know you're probably thinking, we just talked about alpha, beta and gamma, different values, okay? They mean different things. We'll be showing that they use the same values, okay, but then we're talking about different things. We're talking about angles here, okay? And it means then that we have cos of alpha equal x over the square root of x squared plus y squared plus z squared, or x over the modulus of r. Okay, cos of b is y over the square root of x squared plus y squared plus z squared, which equals y over the modulus of r again. And cos of gamma equals z over the square root of x squared plus y squared plus z squared, which is equal to z over the modulus of r. Okay. The other thing that we can say, is that our cos of alpha, cos of beta, and cos of gamma are called direction cosines. So our vector A is equal to cos of alpha I plus cos of beta j plus cos of gamma k. And we can say from that cos squared of alpha plus cos squared of beta plus cos squared of gamma equals 1. Okay, so there's a little bit there. Okay, so we'll have a look at a worked example so we can get our head around this a little bit. Okay, so we want to find the angle to the nearest degree that the vector 2i minus 3j take 4k makes with the z-axis. Okay, so it's saying, well, our a equals our 2i take 3j take 4k. So our modulus of alpha is going to be square root of 2 squared plus negative 3 squared plus negative 4 squared, okay, which is going to be the square root of 4 plus 9 plus 16, which equals the square root of 29. Okay, so our cos of gamma equals because we want our z, okay, well we need to do our z value, which is negative 4, over square root of 29. Okay, so then our gamma value would equal the inverse cos of minus 4 on root 29. And when you work that out, it's 137.97 degrees. Okay, and to the nearest degree is 138 degrees. Okay, so we're getting there. Okay, we're getting there. So we need to talk about column vectors. Okay, so vectors have similar properties to matrices, so we can represent them as matrices. So we say that I is equal to the column vector 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. Okay, so that means then that we can say that our vector OP is going to be given by x1 times 1, 0, 0, y1 times 0, 1, 0, and z1 times 0, 0, 1, which is equal to our x1, y1, z1. Okay. We can then do addition of matrices or multiplication of matrices and that sort of thing for these types of problems. So I'll have a look at one last worked example. Okay, I'll flip over the page because I might run out. Okay, so we've got given the vectors represented as A equals 4, 5, minus 5, B equals 5, 3 and minus 2, and C equals 3, 7, minus 8. Okay, show that points A, B and C are linearly dependent. Okay, so we need to show that they're linearly dependent. Okay, well we can see from here, okay, that vector A, which we can say, let's just call it lowercase a, can be 4i plus 5j take 5k, and B is equal to 5i plus 3j take 2k, and C is equal to 3i plus 7j minus 8. Okay? And so that for them to be linearly dependent, then it's got to satisfy C equals some value alpha A plus beta B. Okay, so we're going to write the equation in matrix form. So we can see then that we've got our 3, 7 minus 8 is equal to some value alpha times A, which is 4, 5 minus 5, plus beta times our B, which is our 5, 3 minus 2, Okay, so that means then that our 3, 7 minus 8 is equal to 4 times alpha, 5 times alpha, and minus 5 alpha, just by multiplying through by alpha. And similarly, this one's going to be 5 beta, 3 beta, and minus 2 beta. Okay, and when we actually do that addition, well, we can say that we get 4 alpha plus 5 beta, 5 alpha plus 3 beta, and minus 5 alpha take 2 beta. Okay, so basically then we can set up our three equations and say, well, we've got 3 equals our 4 alpha plus 5 beta, 7 equals our 5 alpha plus 3 beta, and that minus 8 equals our minus 5 alpha take 2 beta. Okay, so when we add these two, so we're saying that this is equation 1, 2 and 3. Okay, if we add 2 and 3 together, we're going to eliminate alpha. Okay, and we're going to get then beta equals -1. Okay, so then we can say our 5 alpha equals 7 take 3 beta. Okay, so our 5 alpha is going to equal 10 when we sub in -1, so alpha is going to equal 2. Okay, and then we can sub in both our alpha and beta. Okay, so we can see that if we sub in our alpha and beta, okay, then we can see that our right hand side equals our left hand side, so that C does equal 2A take B. Okay, and which means that we are going to be linearly dependent. Okay, we're going to be linearly dependent. So I know this was a long section, okay, and there's a fair bit to take into, so look, you might need to watch this video again. There's a fair few questions to have a crack at too in this section, so hopefully you get through it okay.